Hello, welcome to chapter 5. We are going to dive headfirst into algorithms today. So strap in and let's get going. So, some of the things I added a new slide, some of the things we're going to talk about today is we're going to go through all of the sections in chapter 5. It's an important chapter. So, we're going to go through the concept of an algorithm, the representation. We're going to talk about discovery about algorithms and iterative structures, recursive structures versus iterative. And then finally, we're going to go into the efficiency and the correctness of algorithms. So the concept of an algorithm, now we defined an algorithm as a set of steps to define how to do something prior, probably chapter one-ish. But this chapter is really going to do the deep dive and look very closely at specifically an algorithm. So remember, we talked about algorithms when we converted between bases. We talked about doing the different steps of a magic trick, and those were all algorithms. Some researchers do believe that every action that a human performs is the result of some type of algorithm. So let's finally get ourselves to an official definition of what an algorithm is. So, an algorithm officially is an ordered set of unambiguous, executable steps that defines a terminating process. A lot of big words, but we're going to break it down super, super simple. So, one thing to notice is that your steps need to be ordered. Okay, there has to be some kind of order to these steps. The other thing to see and notice is that it has to have a terminating process. So it has to have an end. There has to be some kind of agreed upon when I actually complete and finish. First, let's take a quick look at the ordered steps. We can put steps in orders in many different ways. We can do it sequentially, like in or linear, where it's step one, step two, step three. It's one step right after another, just in a straight line. We can also do it parallel, and this is doing multiple steps at one time. This is going to require those multiple processors we talked about earlier. I believe it was in chapter 2, but you can do more than one at one time. And then finally, what you can have is something called a cause and effect, and that is going to determine the steps that you perform. So let's look at that process ending, that terminating portion of the process. The requirement of the process is that it must terminate. It's in the definition. This means that your algorithm has to have an ending point. There has to be a point in which you can say, yes, we are now complete. Now, sometimes you can have an application that does not terminate, such as something used in the medical field like a heart monitor, right? It's just going to keep monitoring that heart rate. You can make the argument, though, that that really is just a repeating algorithm where your result is the display of what the heart rhythm is. Okay, so you can see that even though we can look at it as unending, it does have an end. Now, any process that would not produce an answer, that would be considered the non-terminating. Okay, so something as a division problem that has no end, or things like that. Let's take a quick look at the abstract nature of algorithms. So we're going to talk about some of the terminology that we use. So first, there is a difference between an algorithm and its representation. Now, just like there's a difference between the story and the book. Okay, that's the analogy I'm going to use. The algorithm would be the story, what you want to say, what you want to do. The representation, on the other hand, that's the book. That is the implementation of your algorithm. So the book is the implementation of your story. So notice that there is a difference. So, for example, a program is the representation of the algorithm. Your algorithm is going to say in words, in English, what you're trying to do. And the program is going to be very specific in nature and have very special syntax and language to implement what you want to do, or that algorithm. Lastly, a process is the activity of executing the program. But since the program is the instructions for the algorithm, we can actually say that the process is the activity of executing the algorithm. Let's take a quick look a little bit closer at some algorithm representations. Now, algorithm representations, it's done formally for well-defined primitives, okay? You want to go back to those basic building blocks. So it's a collection of primitives within a programming language, okay? So it's done informally by using something called pseudocode. Pseudocode is something between what we speak in spoken English and an actual formal syntax of a programming language. It's kind of somewhere in between. So we can say in pseudocode, say, if this happens, I want this to happen. And then your formal would be representation would be whatever language you choose and the syntax in order to implement that. So let's take a quick look. A good example here is this origami. You start out with the very basic principle of a paper, and you've got some different um, symbols and things. So what do those symbols look like? So, we've got some syntax and we have semantics. Those are going to be the two different things, right? Your syntax is going to be what that language expects to see. That's going to be those keywords when we were typing in Python, the word print, things like that. Now, the semantics is going to be how you would actually explain that to someone using words. Okay, so you're going to use that spoken word. So your syntax might be that loop-de-loop with an arrow, and the semantics is going to tell you turn your paper over. Okay, so it's going to be like a shorthand way of telling you to turn your paper over. Now, let's look at the steps that we go through in order to design a pseudocode language. Again, pseudocode, remember, it's somewhere between spoken English and formal syntax, but it's just kind of in a gray area. You can choose a common programming language, and that can be your pseudocode. Typically, that's where you start, then you loosen up some of those rules, okay? You loosen up the syntax, you make it a little bit more freeform, you allow for some additional natural language as opposed to that hard, a very rigid syntax. You're going to use consistent, concise notation. Think of an outline, okay, as if you're writing a paper. We're going to use something that we're going to call a Python-like pseudocode. So if you were to look at the pseudocode and then have to program it, it's going to translate a lot easier. So let's take a quick look at some pseudocode that we can discuss. So some primitives in pseudocode. Now, when we say primitives, we're saying those basic structures, the basic things we want to do. So some of the basic things we've done so far in Python is we've done assignments where we set a variable equal to something. So a pseudocode would just be writing that out. The variable equals something else. So for example, my remaining funds is going to be equal to my checking balance plus my savings balance. Easy peasy. Let's look at conditional selection. So this is going to be if something happens, I want you to do something else. Okay. So for example, if my sales have decreased, then lower the price by 5%. That's going to be the pseudocode. We'll see later on that the Python is going to be very similar, but you can see right away that right here where it says sales have decreased, you can't actually do that. That's not a variable. It's got, spaces and things. So that will have to be cleaned up. And the same thing, lower the price by 5%. We are doing a combination of the Python syntax and English. So the if, the parentheses, the colon, that's the Python part. The sales have decreased and they lower the price by 5%. That's that natural language. Let's take a look at a conditional selection. So this again is an if condition, something's going to happen, else something else is going to happen. You've got that Python portion in the if and the colon and the else in the colon, and then you've got where it says activity and condition, that's your human language. So for example, if the year is a leap year, I want you to divide it by 366 days. Otherwise, divide it by 365 days. Okay, so that would tell you how many years. Let's look at a repeated execution. So this would be something that you want to do multiple times. You want to repeat it. We're going to, for this one, there's a while, and whatever the while is, you're going to give it instructions. So while you still have tickets that you can sell the tickets. Okay, very, very easy. So that'll keep doing, it'll keep selling the tickets until there's no tickets available, and then it'll stop. So that's kind of a good way to look at that. Now let's look at some of the, if you start, so there's something called a nested condition where you can put some of these ifs and loops and things within each other. Good programming structure tells you that if you're going to put these things within each other, we're going to add that white space. Now remember, white space and comments completely for the users. It has nothing to do with the compile, it has nothing to do with the program, completely for the user. So you might as well use it. So good programming technique tells us that if we're going to put, for example, here an if else within the if portion, see how it's indented to the right a little bit more so that that if and else that go together are lined up. And then you can see going a little bit out to the left, that if and else are lined up, and that means those two go together. So you can see very, very easily visually what's going on. Now let's take a look at what it's saying. So it's saying if it's not raining, if the temperature is hot, go swimming. Otherwise, go play golf. Well, okay, that sounds good. But what if it is raining? Then that comes down to that else, and it says, I'm going to watch TV. If we want to define a function, we can just say define the name. So for example, define process loan. Now, if we want to execute the function, we just call the function. So if something happens, I want to process the loan. Otherwise, I want to reject the application. So let's take a quick look that was in the book, figure 5.4 at a procedure greeting in pseudocode. So we define our procedure and our function, and it's called greetings here at the top on the top line. Then we're going to do a few things. Now you can see again with this white space, everything it's going to do is lined up. Everything that is contained within this while is lined up. Again, good programming practices. So the first thing it's going to do in this function, it's going to set the count to 3. And then while that count is greater than 0, it's going to print hello. It's going to subtract 1, and then it's going to keep going through. So it's going to print out hello, hello, hello. So using parameters on the pseudocode, what we can do is we can define we can define our function and give it the parameter there. Here, for example, we have the list of parameters. And so, for example, if we define a function called sort and we send it a group of data, we can have it sort through the data. So this on the bottom half, it would execute the sort on various different types of lists. So the first one would execute the sort on the membership list, and the second one would be on the wedding guest list. Let's take a little bit of a break and take a look at algorithm discovery. So the first step in developing any program is to figure out what the algorithm is. It is more of an art than a skill. It does take a sort of finesse to figure out what those steps are and what order to put them in and how to arrange them. So it is definitely a challenging task. So one of the ways that we can go through and figure out what those algorithms can be the Polya's problem solving steps. Now, the basic steps to problem solving is 1, understand the problem, 2, devise a plan for solving the problem, carry it out, and then see if what you decided to carry out worked, basically. And you can then iterate if necessary. Now, we can take these basic problem solving steps and apply them into the program development world. So, number 1, understand the problem. Nothing has changed there. But step 2 is going to change a little bit and transform into get an idea of how the algorithm is going to solve that problem. How is it going to work? How is it going to function? What is that algorithm going to look like? Once you figure out that step, then you can formulate the algorithm and represent it as a program. So you can go from that algorithm to the representation, right? Finally, the step that's always the best one is to evaluate the decisions that were made, see how they work, see if they're accurate, if they have any potential issues, and see if this is going to be a successful solution. So you can take those normal problem solving steps and translate them into how to program very, very easily. So, how do I start though? Where do I even begin with? So try maybe possibly working the problem backwards. Start at the end and figure out how to get there. You can solve an easier problem, especially if it's related. Um, you know, Relax some of the constraints. See if you can solve that and then implement those constraints back. Solve the problem piecewise. So it's called a bottom up methodology. You can break it into smaller pieces. Once part A works, move on to part B. Segment it. Makes it a little easier sometimes. And then sometimes is a stepwise refinement, dividing that program or the problem into smaller problems and doing a, top down methodology. What is my most difficult problem? What is the easiest problem? Maybe even, divide it in that way, shape, or form. So here we've got an example that we can look at. Um, we want to figure out the ages of some of our kids. Okay, this is gonna be a word problem. Don't shut off on me, please. So person A is charged with the task of determining the ages of B's three children. Okay. B tells A that the product of the children's ages is 36. Okay. A replies that another clue is required. B tells A the sum of the children's ages. A replies that another clue is needed. B tells A that the oldest child plays the piano. Does that have anything to do with anything? Probably not. So A tells B the ages of the three children. So how old are the three children? So we've got all this information here. What are we going to do with it? Well, we can look at the very first part of this that says B tells A that the product of the children's ages is 36. So right there, that actually narrows down our infinite number of ages down to a select group. So the first thing we're going to do here is in graphic A is we're going to find all of the numbers that when I multiply them together is going to give me the number 36. Okay, so we went from an infinite number of pairs down to 8. Okay, so we've got 1 1 36, 1 2 18, 1 3 12, 1 4 9, 1 6 6, 2 2 9, 2 3 6, 3 3 4. Okay, that could be part A. Just taking that one piece of information, that one little clue, and applying it. The next part of the clue that we have is that B tells A the sum of the children's ages. So now what we can do is sum those pairs or triples, sorry, that we came up with and get the sum. Okay, that's what this portion does. Okay. So you can see that if you knew the sum of, let me go, there we go. If you know the sum, there's a duplicate between the 166 and the 229, but all the other ones are unique numbers. So if you know the sum, you know the ages. So if I were to look at this and I were to look at this, I would say if A knows the answer, if the A if A knows the answer after just that information, we get rid of those duplicates. Okay. So it doesn't mean it has nothing to do with those. So narrows down your options much, much more. Okay. So hopefully that gave a little bit of an insight into how you can just break it down into much, much smaller steps so that you can understand and implement it fully. Now, an iterative structure is going to be something that's repeated. It is also sometimes called a loop. Um, there are different ways if you want to repeat a digit, if you want to do our examples are going to be some sorting algorithms because you're going to look through a list many, many different times and sort it to see if you can find what you're looking for. But just think of it, any kind of step that you want repeated over and over again, that's what's going to be an iterative structure. So here's an example out of our book of a sequential search algorithm. Again, we're going to use pseudocode here. So remember, it's Python-ish, but it is a little bit easier to understand if you were to read it out loud. If you need to read it out loud, that's fine. Okay, so the first line says I'm defining a function. It's called search. I'm going to send it a list and a target value. Okay, look how nice the lineup is. You know, that if you can tell goes with that else, that while goes with that if with that else. You can see everything's all nice and lined up. You can definitely see right off the bat without knowing too much about programming what's going with what. So the first thing we do in this list is if the list is empty, then there's no sense in going on, right? So if the list is empty, we're going to say the search failed, we couldn't find it, and just we're going to stop. If the list is not empty, we're going to select the first entry in the list to be the test entry. Okay. While my target value is bigger than my test entry, and we still have entries to look at, select the next test entry as test entry. So what it's doing is it is going through that list and taking the test entry to be whatever is the next one in the list. If what I'm looking for is the one that I found for test entry, then I found it. Okay, so I'm going to declare the search a success and I'm done. Otherwise, your search is a failure. Okay, it's going to keep going, okay, in that while loop, and it's going to repeat. Okay, that's that iterative. While that target value is bigger than the entry value and you still have records to look at. Once you've gotten to the end of the records, there's no sense in looking. And once you found it, there's no sense in looking, okay? So that's how you kind of would do that iterative structure by repeating things over and over again. The big three components when we're looking at iterative or repetitive control is you need to initialize, you need to test, and then you need to modify. When you initialize, you're establishing a baseline. When you go into that iterative structure, it has to have a value in order to start. You have to give it some place to start. That starting position is what is going to be modified going forward. Okay. Test condition. This is where you need to be able to get out of that iterative structure or that repetitive structure. So it's going to compare the current state of whatever you initialized to something. If it is greater than something or less than something or equal to something, okay, that's what you're going to use as your iterative. Okay, as long as you pass that condition, it's going to keep doing the iterative structure. Once it fails, it's going to stop. Finally, whatever that is that you use to initialize, you need to modify it because you remember if you're doing some kind of comparison, if you need to add one to it, you add one. If you need to subtract one, you subtract one. But you've got to do something to it. Otherwise, it's just going to keep doing whatever instructions you gave it forever and ever. It's never going to know to stop. There are two different kinds of iterative structures. There's a pre-test and a post-test. Now I've got images here of both of them in a flow chart. They look relatively similar, but you can see here on the left, this is the pretest. The test happens in front of the body. Coming out of the test, you go into the body and then you either loop back to the condition or you exit out if false. The one over here on the right, this is doing the execution first and then testing after. That's a post test. So again, post test is testing after. So for the pre-test loop, it is considered a while loop. So while my number is less than 10, I want you to do something. While I did not find my name in the list, I want you to keep looking. A post-test loop is going to do something first and then do the check. So what we do is we use something called a repeat until. So in this case, we have repeat body until. So repeat. So keep printing a number I'm giving you until the number is bigger than 10. So that's the real difference between the two. In this example, we've got sorting the list Fred, Alex, that one, Diana, Byron, and Carol alphabetically. So our initial list just has a gobbledygook of all of these names. They're not in alphabetical order. There's nothing like that. So the first thing it's going to do is it's going to look at the very first record, Fred. Okay. It's going to say Fred is now sorted. That's what's happening on this first line. So then the first line takes the next value down, which is going to be Alex. And then it's going to say who comes first, Fred or Alex. Okay. I'm just working my way across that top line. So Alex is going to come first. So it's going to move Alex and put it in front of Fred. So now our sorted is going to be that lighter shaded, and it's going to be Alex and then Fred. And then the rest of our data is going to be down below it. The next step it's going to do, now I'm on the second line, I'm on line 2 right here on the bottom. I've got Alex and Fred sorted. It's going to look at Diana. Diana's the next one in the list that's left below it. And where does Diana belong with Alex and Fred? Does Diana belong before Alex? No. So it's going to look at Fred. Does it belong before Fred? Yes. So it takes Diana out, moves Fred down, and puts Diana back in. Okay. On the third line, we're now going to look at Byron and decide where Byron goes. Does Byron go before Alex? No. Does it go after Alex? Yes. So Byron gets moved out. Everything after that that has been sorted is moved down, and Byron is inserted into the list in its proper location. Finally, we're down to Carol, and where does Carol go? Does Carol go before Alex? No. Does it go before Byron? No. Does it go before Diana? Yes. So Carol gets pulled out, everything that is sorted below it gets shifted down one, and Carol gets put back into the list. And then your list is sorted. Okay, so you can see how it keeps doing the same thing until it finds what it needs, and then it does something else. So it's kind of how that repetitive structure is going to work. This is going to be the insertion sort algorithm, which is what we just walked through. It's called an insertion sort because you're inserting whatever value you have into the proper location when you sort it. This is what it would look like in a pseudocode. Remember, pseudocode somewhere between that real life English and, the hard language of whatever you're programming. So we're defining a sort, we're sending it a list. I'm giving n, which is a number, the number 2. So while that number, okay, so your initialization is that n equals 2. Remember those 3 steps: initialize, test, and then modify? Now I'm going to do the test. While n is less than or equal to however many number of things I have in that list, I'm going to take the value out, and I'm going to put it somewhere else. I'm going to put it in pivot. I'm going to remove the entry that the hole left by taking pivot out. Okay, so while there's an entry above the hole and whatever entry I have is bigger than pivot, we're going to move the entry down, leaving the hole. So we're scooting everybody down. Okay, we're making room for where we want to put that new value. Then finally, we're going to move pivot, which is the value we want, into the hole. Next, we're doing that modify, n equals n plus 1. Okay, so we did our initialization, n equals 2, our test, n is less than or equal to the length, and then we did our modify, n equals n plus 1. You don't need to get involved in the weeds in this, just kind of let it wash over you and just kind of get the main points of it. Let's take a look at the recursive structure. So you are repeating these instructions. You could look at it as a subtask. You can look at it in many, many different ways. So multiple activations of the procedure are formed, all but one of which are waiting for the activations to complete. Okay, so the only one that it's going to stop once it's complete, and then it's going to complete everybody else that came before it. So example that we're going to look at real quick here is a binary search algorithm. Now, applying our strategy, what we want to do is, so say we have an original list of a bunch of names and we want to find a specific name. What we can do is break it up into a sublist. This is more of like a tree structure. So I'm going to take the list, I'm going to break it up into 2 halves. So I've got the first half starting with Alice, the second half starting with Irene. So I'm going to look for John. Now, is John going to come in the section that is Alice or the section that is Irene? It's going to come in the section that's Irene because J comes after I. So you're going to take that sublist now and create a second sublist. Okay, so you see how we're taking this list and dividing it in half each time? Eventually, you're going to either find what you need or you're not going to find it and you can stop. So in this case, instead of doing it sequentially, which you would check Alice 1, Bob 2, Carol 3, 4, 5, 6, 7, 8, 9. I would have to check 10 entries if I was going sequentially. In this bubble sort strategy, I only have to check 1, 2, 3 times and I have it. So you can see how you're doing a lot less steps. A first draft of doing this binary search technique. So if the list is empty, we're going to stop. We're not going to do anything. Otherwise, we're going to take our test entry as that middle value in the list. Remember, I said we're going to keep dividing this list into 2 until we find what we need. If the target value is equal to the entry, then we've found it. If it is less than, we want to take the preceding portion of the list. If it is greater than, we want to take the portion after the list. Okay, so let me go back one slide real quick. So I'm in my middle. If it is less than, I want to take this part for over here, but if it's greater than, I want to take that portion. Okay, we're going to keep doing these things over and over again until we find our value. So that's the easy part. Now, let's look at that binary search algorithm in pseudocode. So define your search, your target value. If it's failed, okay, take that middle entry. This looks very, very similar, right? If the target value is equal, we've found it. If it's less than, your sublist is going to be the preceding portion. If it is not, it's going to be the portion following. Okay, again, we're going to take that list and divide it again. So you can see how you're going to keep using the same thing over and over again. Recursively searching, again, you're just going step by step, trying to find a value that you're looking for. Okay, you are doing the same tasks over and over again. So that's why you've got your ifs and your elses. You've got your ifs with some equalities in there. And if you found it, you stop. If you haven't found it, here's your steps to set up for the next search. So you're going to set up those lists and decide what you want to do. So this just goes through. There's the second time that it goes through. It takes that second portion of the list. And eventually you will find your value. So you'll run through it once, you'll run through it twice, and then eventually you'll find either the value you have or the value doesn't exist. Now, let's get away from all that. Recursive control. So the way that you control these looping functions and these repeating function is that you've got to have, remember, I said there's an initialization, a modification, and some sort of test case or a termination. It's going to provide the illusion that it's making multiple copies of the same thing, creating kind of like a stack of all these things that are happening at the same time, but only one copy is actually running, the one that you are currently in. Eventually, the others are waiting to see what the result of that is. If the result is I didn't find it, then they're all going to close out and say didn't find it. If the result is I found it, they're going to hand that value back. Okay, but it is going to look like I'm starting this one, and then from that, I'm starting a copy of it, I'm starting a copy of it, I'm starting a copy of it, and then they're all going to collapse down. In reality, you're only running whatever is the one in focus. Last but not least topic for this lovely lecture discussion is efficiency and correctness. So, there is a choice sometimes you have to make between efficient and inefficient, but sometimes it can push you over the edge to correctness and, incorrect or practical and impractical. So the correctness of an algorithm is determined by reasoning formally about the algorithm and not by testing its implementation. You know, basically what you have to look at is does this make sense? Is this feasible? And what am I losing by making it more efficient? In a nutshell, that's all that's really saying. Your efficiency can be measured in many different ways, but typically it's in the number of instructions executed or the number of times something is executed. When I did that original search for John, I counted 10 times versus the 3. That's how you can look at efficiency. It uses this theta notation, which is a Greek letter, theta, and it would be in theta of n to some value. A lot of times it's you need to incorporate the best, the worst, and the average case. Okay, so you do want to take in those outliers when you are looking at efficiency, but most of the time you the average is what is good enough. Now, in a worst case scenario, you need to look at every single value in that table, right? That's in essence, that's what a worst case is. This just gives them some information. So you're looking here, you've got a pivot. And in this worst case scenario, as you can see, it is actually alphabetically backwards. Okay. So your A is at the bottom and your E is at the top. So in worst case scenario, what you want to do is basically flip that entire list. So that's what this is showing you, is just that in a worst case scenario, this type of search can complete within the 4-step process. So software verification, we can use proof of correctness with formal logic and assertions, preconditions, and loop variables and such. Testing is more commonly used to verify software than to actually analyze the effectiveness and the correctness of it. Testing is only going to prove that the program is correct for those test use cases. You can't prove that you're going to be correct for every single outlier. Usually that's what beta testing is going to be for. So let's look at a quick problem, a chain separating problem. Again, word problems, don't freak out. A traveler has a gold chain of 7 links. He must stay in an isolated hotel for 7 nights. The rent each night consists of 1 link from the chain. So what's the fewest number of links that must be cut so that the traveler can pay the hotel 1 link of the chain each morning without paying for lodging in advance? Okay, so let's look at this chain. So we've got a 7 link chain. Okay, we need every night to have a new link. So we can use it to cut 3 different ways, right? 1, 2, 3, 4 nights. Well, on the other hand, I can do 1 cut to solve the problem, but they are all linked. So you would be doing that prepay. Again, there are so many different ways to solve these problems and different ways to look at these algorithms, because that's all the algorithm is. Remember, it's the process and the steps that you need to solve a particular problem. It's just what costs do you want to pay for it? Okay. This one solved the problem with 1 cut, but you do have the prepay, whereas the one in the previous graphic did it in 3 cuts. So the very last thing that we're going to look at is we're going to look a little bit right here at this graphic at a flow chart. So typically these are the typical looping structure is going to have some things that look like this. There is your initialization in your first box. You're going to start out with some kind of precondition. Something's going to be there at the beginning. You're going to initialize some variable. You've got your test, which is always the rhombus or diamond shape, and that's going to be your test case. If it is true, you go to the body. Within that body, you've got to modify that initialized variable. Okay, that's considered the loop variant or the loop invariant. Okay, if the test is false, it's going to go out there to the right, and the termination condition applies, and you no longer have anything to do. But you've got to remember those 3 steps: initialize, test, and modify. That's all there is to today's lecture. So good luck on your knowledge check and on your assignments. And as always, if there's any questions, please let me know.